All right. So we are going to just finish off the thermodynamics unit today and start the electrochemistry unit. I do want to start a demonstration, and so that's what I'm going to do right now at the beginning of class. It's actually electrochemistry, but I've got a few demos for next week, and I saw this online, and I'm like, that's really cool. So let's go set that up, and then we'll come back and continue the course material, because it does take a little while for this reaction to complete. I know there's bars. They should go away in just a few seconds. So if I'm right, there is video. Yes, there is video feed. Excellent. Good. So I'm going to need to put on some gloves for this, so just bear with me while I get appropriate PPE on. Because, of course, Coca-Cola is a very dangerous product, as one would expect. So we have here, of course, Coca-Cola. Coca-Cola and most pop is packaged in aluminum cans. Now, aluminum, I mentioned previously, but I'm going to restate here, aluminum is different than iron. It's actually more reactive than iron. But whereas when iron forms iron oxide, the rust flakes off, exposing more of the iron metal to continue oxidation. However, aluminum doesn't do that. When aluminum oxidizes, it forms a layer that binds very strongly to the aluminum surface. So the outside and inside of this can have aluminum oxide that is protecting the aluminum. And I can expose the aluminum by just kind of sanding the outside edge. That's going to take a while. So there's one that I've already done right here. And in the time that it took for me to sand this before class and now, another aluminum oxide layer has formed. That aluminum oxide layer is actually only stable under normal ambient conditions. If it is exposed to strong acid or strong base, that aluminum oxide layer actually doesn't form, and you're able to see the reactivity of aluminum. So what I have here is a strong basic solution, and I'm just going to remove the oxide layer that's on the outside and put this in. We can then zoom in on it. And I'll even move the camera to try to get closer. And you should be able to see that there is a reasonable reactivity. There's bubbles forming around the aluminum can as the reaction is proceeding. So that reaction is going to slowly eat away at the aluminum, well, much faster than normal. And what I didn't tell you is that the inside of the can is filled with pop. Pop's got a pH of about 4. The inside of the can would actually slowly eat away at the aluminum as well, except to prevent that, the manufacturers put a little plastic liner on the inside. With luck, we'll be able to eat away the aluminum and keep the plastic liner, hopefully. So that reaction is going to proceed, and it's going to proceed during class, and we will actually be able to monitor it. But I'm just going to now continue with the course material. Is that better?
You can see the reaction. There's lots of bubbles forming, and you don't have to worry about how bad it is for you. So that being said, the price of, it's funny you say that, Benjamin. When I went to buy, I don't drink pop at all, or very, very rarely, not even at parties. I'm more water or juice. Juice is bad for you too. But the price of individual cans of pop is through the roof. So I had to buy a case of pop. Cheers. I'll hide the label from you, which makes it hard to take a drink from. Whatever. Better than booze, William. So anyway, I do have a lot of pop left over. And so the joke that was in the first class was that they were talking about having a pizza party. And I said, great, I'll bring Coke. And then I thought about what I said. And then I said, yeah, I'll still bring Coke. All right, let's continue with the course material. All right. I also modified the display sheets here, or the camera system, to put the Coca-Cola reaction on the top, so we can monitor it as we go through this the course material. Anyway, this is what we did last day. We finished off looking at the idea of complete reactions. In the sense that equilibrium implies that you have some reactant and some product at equilibrium, such that you could actually shift the equilibrium one direction or another. And what I told you, but I've all done the calculation on it, is that beyond about plus or minus 400 kilojoules, the reaction is so complete that either you go all the way to completion, that is not one molecule of reactant remains, that's delta G is less than minus 400, or on the other side of it, when delta G is greater than plus 400, no reaction occurs at all. Not one molecule of reactant actually goes to produce product. So that would be a complete reaction, delta G is less than minus 400, or no reaction occurs when delta G is greater than plus 400 kilojoules. Okay, so that's where we ended off last day. We also now have the ability to derive an expression, an equation that expresses the equilibrium constant as a function of temperature. When we were doing equilibria at the beginning of this course, I mentioned that equilibrium constants were temperature dependent. We're now at the stage in the course material where we can actually prove that and also calculate equilibrium constants. And so that's what we're going to do right now. So we have two equations for delta G. Minus RT ln K. We also know that it is delta H naught minus T delta S naught. If we equate these two parameters, we end up getting that expression right there. And I'm just going to move the negative sign to the top. The natural log of K is equal to negative delta H over R T plus delta S over R. That is the relationship we want. And if you look at this, we have information on the relationship between natural log of K versus 1 over the temperature is linear. And I had already given you this information, but for the lab, but for here, the slope is equal to negative delta H naught over R and the intercept is delta S over R. And we're going to use that in one of the examples we see in just a few minutes. So that's the relationship we have right there. And one of the other things that we did in the equilibria unit was I asked you to calculate the pH of neutral water, where we had a Kw at 298 Kelvin. I also asked you to calculate the pH of neutral water at 310 Kelvin, if you go back in your notes. And I gave you an equilibrium constant, and I said, we'll be able to calculate that equilibrium constant in a little bit. Well, that little bit is today. So now we're going to go through and calculate, excuse me, Kw, verify that value at these two temperatures. So the reaction that we need is that of liquid water autoionized to that. We're going to need delta H of formation and the absolute entropy of these entities. I want to point out that these values are not on the data sheet. They are on the two-page data sheet. They are on the extended data tables that I have uploaded to Blackboard. So they are on the extended data tables if you need to look these things up for aqueous solution. Anyway, the values that we have, I'm just going to give them to you. Minus 285.8, 0, and negative 230.0 kilojoules per mole. 69.9, 0, and negative 10.8 joules per mole Kelvin. You have calculated already, done several examples calculating the reaction enthalpy and the reaction entropy, and it is 55.8 kilojoules for the reaction enthalpy and negative 80.7 joules per Kelvin for the reaction entropy. Good. The relationship that we need is, of course, delta G is equal to minus RT natural log of K. And the other one we have is delta G is delta H naught minus T delta S naught. What I would like to do this is in two steps. I would like you to go through, and this is the trick here. If your family name, your last name, is in the A to M range, if your family name is in the A to M range, I'd like you to calculate delta G naught at 298 Kelvin and K at 298 Kelvin. If your family name is in the N to Z, I would like you to calculate delta G naught at 310 Kelvin and the equilibrium constant at 310 Kelvin. The only other equation that you probably are going to need is to realize that K is equal to E to the minus delta G naught over RT. That would be that rearrangement of that equation. So go through, do that, and plug your values into the chat, please. And please plug them in when you get them so that other people can verify their values and move forward to calculating the equilibrium constant. Thank you. Up or down? Oh, Yeah, you went down. You mean down. Okay. Yeah. Got it. I'll give you that other equation. There it goes. I'll wait for two people to verify numbers, and then I will just write it down. So if someone can verify Haley's G, yep, Alexander got the same value, I'm assuming. I'm actually going to give it to one more significant digit, just because it's 85, 79.85 kilojoules. I'm going to put it in a different color too. And now either the equilibrium constant at 298 or G at 310, please. No, G at 310 is 80.82. That's correct. Remember, in calculating the equilibrium constant, you need to convert to joules, get your so that your units cancel out properly. There we go. Right. Remember, this is in kilojoules, and R is in joules, so you need to convert to joules. So the K at 298 Kelvin, as one would expect, is 1.01 times 10 to the minus 14 with units of moles per liter squared, just by looking at the equation, which is good. How about K at 310 Kelvin? Anyone? 2.4 times 10 to the minus 14. Good. 2.41 times 10 to the minus 14 moles per liter squared. And in terms of significant digits, they're known to, at best, one significant digit. So these numbers afterwards are estimates. So using equilibrium constants to two significant digits is reasonably valid, realizing that the second digit is iffy, but more than two significant digits, just not possible. So that is how these are calculated. And it verifies, if you go back in your notes, verifies the numbers that we used at the beginning of the term in the equilibria unit. In lab, I asked you to plot the natural log of K versus 1 over temperature, and from that calculate the reaction enthalpy and entropy. That is done here for you for a different reaction, the reaction of hydrogen and iodine to produce HI, and we're asked to determine the reaction enthalpy and entropy. So just to rewrite this equation off the graph, we had y is equal to negative 6347.3. Now the units on the slope are based on the rise over run. Natural log of K doesn't have units, but this is inverse temperature. So it is natural log of, or no units over 1 over 1, or over 1 over T. So the units we have here is 1 over T, capital T, which would end up being simply Kelvin times X plus, and the other value is 19.966. And there doesn't happen to be any units with the intercept because it is the natural log of K. That is the value. There's no units associated with it. As given previously, we know that the slope was equal to negative delta H naught over R, and the intercept was equal to, actually I need more space, was equal to delta S naught over R. That is such that delta H naught is equal to negative 6347.3 Kelvin times 8.314 joules per mole Kelvin. I need to go restart that camera, excuse me. The camera sometimes overheats, so we're back. When we do the math here, we end up getting a value of 52.77 kilojoules. In terms of the intercept, delta S naught is equal to 19.966 times 8.314. And that gives us a value of 166 joules per Kelvin. The moles are ambiguous here, per mole of reaction, or I just have left reaction enthalpies to be per mole of reaction. So the mole comes in and goes out, as we discussed last day. Units. How many people here have taken statistics, or more specifically, know how to get the units out of a graph? Is that something you learned? If you've taken stats here at university, you may have learned it. Has anyone done that? Not yet. Okay. One of the things that you would do is, in stats, haven't learned it. Well, I don't know why. It's actually a fairly, well, it's a common calculation. It's an important calculation to get the slope and intercept. That should reset. There it goes. We're interested in the uncertainty in the slope and intercept. And that camera clearly didn't do what it was supposed to do, because bad things happened over there. All right. So we'll get back to slope and intercept in just a second. let's get some gloves on and go see what has ultimately happened here. Well, first of all, there is pop on my camera. That's bad. And there's pop everywhere, actually. If I go in here and pick it up, it has literally blown out inside. So the video that I saw actually had the aluminum dissolving away and having the plastic liner actually surviving in what is ostensibly a sealed can of pop. Clearly, they must have removed the carbonation beforehand somehow, because what we ended up getting here is a blowout of the carbonation, and we have the aluminum being eaten away to the point where it is ruptured because of the pressure, and we have got stuff everywhere. So let's just zoom out a little bit more and go that there is liquid on the handle for this tripod. There's water dripping from the bottom. There's liquid all through the fuel hood. And if I go up to the, I don't know where I'm at right now. This space right here is dripping wet with pop as well. So it works. We basically were able to eat away the aluminum, and this is what the raw aluminum looks like. Inside is still shiny because it's plastic coated, even though it wasn't there, it's got plastic coating on there. That is the aluminum that has been eaten away to the point where it couldn't contain the pressure. And just give me a second, because someone needs to wash their hands and take off the lab coat. There's Coke on the roof. Yeah, the entire inside of that cabinet is covered in Coke. So someone's got a cleanup job immediately after class. So, all right. That being said, away we go. Sadly, Ben, it's me. Unless you want to come by, I'll give someone a can of pop if they want to come clean a fume hood out. All right, let me remove the, there we go. Oh. I need to make this, hold on. I need to make that go away. And figure out what's going on here. Just give me a sec. I need to reset that connection too, apparently. Ben's on campus. You will for bonus points. I'm giving you a pop. You get a wonderful can of Coke. Okay, we're back to this. Whatever. Back in my day, we volunteered to do things like that. Oh, yeah, whatever. No, we didn't. Uncertainty in the slope of the intercept. Well, in stats, you will eventually calculate it. If you're sticking through science and you take Chem 210, that is something that we would be able to calculate there. We're not going to do it here. So we're going to end up just looking at these values and giving them one decimal place, 3 significant figures. That's about as good as we can get. Reporting them to what we would normally report them to had they been calculated any other way. So 52.77, 166, and I actually don't have the next digit after that. I think it's 0.0, actually, now you mention it. It is 0.0, 5.99, yes. There we go. Good deal. Okay, so we were able to calculate those values. Instead of calculating equilibrium constants from scratch every single time, if we happen to know the equilibrium constant under one set of conditions, i.e. 298 Kelvin, where it's tabulated, well, then we can actually calculate the equilibrium constant at other temperatures, assuming that there isn't a great change in delta H or delta S of the reaction, which is a reasonable assumption to make. I'm actually not going to derive the two-state equation. I'm just going to give it to you. It's often called the Van 't Hoff equation. And we're going to use that Van 't Hoff equation in an example right now. So here we have the dissociation constant of acetic acid, very commonly used, 1.8 times 10 to the minus 5 units of moles per liter at 298 Kelvin. That's what's tabulated. If we're doing a reaction at an elevated temperature, we might need to know what the equilibrium constant is at that temperature. So there's the dissociation equilibrium constant, and I've also provided the reaction enthalpy, which you could calculate by going and looking up the values. What we are going to need to do is look at our equation. 2. That's the Van 't Hoff equation. And we need to just set up our states. So our state 1, for convenience, it doesn't matter which way you do it, 350 Kelvin. State 2 is 298 Kelvin. Just makes the math a little bit easier to do it in this order. If you choose to do it in the other order, you're going to get the exact same final answer. So if we do this and plug our numbers in, that's going to equal, just taking care of the units, 42.7 times 10 to the 3 joules over 8.314 joules per mole Kelvin. And then here again, that per mole just kind of is there. 1 over 350 Kelvin minus 1 over 298 Kelvin. You do all of the math there, and you're going to get 2.56. And that happens to be the natural log of K1 over 1.8 times 10 to the minus 5 is 2.56. In order to get the value of K1, we need to take E to everything. And that's going to give us an intermediate value, K1 over 1.8 times 10 to the minus 5 is equal to e to the 2.56, or K1 is equal to 2.3 times 10 to the minus 4 moles per liter. There we go. K1 is 2.3 times 10 to the minus 4 moles per liter. That's just another way of calculating the reaction equilibrium constant. If we happen to know it at one temperature, we can calculate it now at another temperature. Does anyone have any questions on the calculations that we've just done? We've done a few examples. Are there any questions on those examples? Good. All right. Can I show the answer again? Sure, just give me a second here. Should have left it on this page. I will be giving a summary on the thermodynamics unit in just a few seconds once we're done this page, but I'll tell you that we are done the thermodynamics module. And now that we're done the thermodynamics module, the problem set, you can do all of the questions on the problem set. There is not going to be a problem set quiz for this module simply because I don't have access to the Hayden McNeil servers anymore, or you don't have access to the Hayden McNeil servers anymore. So I will be posting the answers to the problem set in a little bit later this weekend, but it behooves you to work on them without looking at the answers. Benjamin, no, it can't be on Blackboard because each problem set quiz is about 80 or 100 questions that are of all different calculation and numbers, and Blackboard doesn't allow me to import the questions I've already created. So just logistically says it's not feasible to do it at this time. And the university is actually moving. The other reason is the University of Northern British Columbia is moving away from Blackboard and probably going to Moodle, which is what the Hayden McNeil website is on. So if I could have imported them seamlessly, yes, I would do it. But if I had to recreate all the questions, which I would need to do, that's several days worth of work per quiz. So in summary, we have a spontaneous process is something that occurs by itself. It does not need outside energy or influence for the reaction to occur. We introduced the concept of entropy, which is a measure of the dispersal of energy. The system entropy, which is something that we can conceptually consider and also calculate. But in general, the system entropy increases when you add heat. It increases the temperature, makes more energy levels available, more energy available. And when there's a phase transition from solid to liquid to gas, you go from just having vibration to having vibration and rotation and translational freedom. When the system does work, the volume increases. So like in the expansion of a piston in a cylinder, it expands the volume. That's doing work to drive the engine forward. That's, if you're in engineering, that's called PV work, pressure volume work. But when a system does work, the entropy increases. And when a reaction occurs, if you increase the number of entities, you're going to increase the system entropy. The entropy of the universe is our spontaneity predictor, okay? Difficult to calculate what the entropy of the universe is for every reaction, but we can calculate the Gibbs free energy, which is proportional to the universe entropy. It is actually the maximum universe entropy available. So in the context of application, the Gibbs free energy is the maximum amount of work we can extract from a system, or the minimum amount of work that needs to be done to a non-spontaneous system to make it spontaneous. And we had a number of different calculations involving delta G. Delta H minus T delta S allows us to calculate it at any temperature. Under non-standard conditions, we were able to calculate delta G non-standard, knowing the reaction quotient Q. And that led us into the connection between thermodynamics and equilibria, and we have a relationship between the standard free energy of a reaction and the equilibrium constant. And then we did a bunch of examples on that, and that actually concludes this unit on thermodynamics. Does anyone have any questions? All right, seeing no questions, just to put the material in the right box, we do have 5 minutes remaining, and I do want to just touch a little bit on the electrochemistry stuff. Can I get everyone to just log off here and log back onto the electrochem section? I greatly appreciate it. We'll see everybody in literally a minute.